Okay, welcome to our Thanksgiving Day class, our online class for Ancient Philosophy, Philosophy 212. I'm just going to give a short lecture that sort of continues on some of the stuff we talked about in last class. So last class we were talking about Aristotle's, what's called the law of non-contradiction. And recall, the law of non-contradiction says there cannot be a sentence that's both true and false at the same time. Now, last time we talked about some apparent counterexamples to this. For instance, if you were to say, well, if you look out the window, I can honestly say it's raining, but there's people in Europe right now who can honestly say it's not raining. But that's not a contradiction because the sentence "it's raining" is being uttered in two different places, and the idea is the law of non-contradiction says you can't have a sentence be both true and false at the same time, in the same place, and all that stuff. We also looked at like the example of, I love her, but I don't love her. In that case, the word love is being used in two different ways, so that's not really a contradiction. Today, I want to look at some examples or possible examples that really do present a genuine problem for the law of non-contradiction as Aristotle thought of it. And all of these examples I'm going to be giving, both today and possibly in our next class after the break, are examples of what are called paradoxes. So a paradox is there's a number of different kinds of paradox, but here's the couple that we'll be looking at. A paradox is something that you seem to have an argument that it must be true, but you also have an argument that it's not true. So you have sort of a case where you have where two apparently good arguments have opposite conclusions. That's what that says. I don't know how well y'all can read it on the video, but it says a case where two apparently good arguments have opposite conclusions. And that's called a paradox. It comes from the Latin for belief, doxa, which is where we get words like dogma in English. It's where you have para, two beliefs that sort of go against each other, like basically beliefs that can't both be true, if we do a bit of etymology on that. The other definition of a paradox, and there are multiple different definitions of what a paradox is basically just something that just can't be true. Something that's impossible, and yet you seem to have an argument that it is. It is true. Basically something impossible that nevertheless seems to be true. Something apparently impossible that seems to be true. And the first paradox we're going to look at is kind of more in the second vein than the first vein. It's just something that just can't be right on the face of it, and yet there it is. What are you going to do about it? And so I'll just, without further ado, I won't ask for any questions since there's nobody here. I'll dive into our first paradox. And it's generally known as the liar paradox. Although it's also sometimes simply known as the liar sentence, or simply the liar. A lot of philosophers just refer to it as the liar. And it's a very simple paradox. By most accounts, it's the simplest of all paradoxes. It's a sentence of English, or of whatever language, it actually works in any language you want to do it in, that simply says of itself that it isn't true. In English, we would say, this sentence is false. Now, this sentence refers to the sentence itself, not to some other sentence. And in this case, we have a real problem, because it looks like if this sentence is true, so if it's true, well, then what it says is true, and what it says of itself is that it's false. So if it's true, then it's false. But if it's false, well, if it's false, then it's not false, because what it says is that it's false. So if it's false, then it's not false. So if it's false, it's true. So if it's true, it's false. If it's false, it's true. Here we have a very simple, and it is incredibly simple, just four words long, apparent counterexample to the law of non-contradiction. A sentence that appears to be both true and false at the same time. Because whichever one it is, it has to also be the other one. So what do? Is there a way that we can somehow explain this sentence away, or argue that such sentences are somehow invalid, or invalid is not the word, but illegitimate parts of English? And indeed, for thousands of years, philosophers thought that there must be something sort of wrong with sentences that talk about themselves. And so maybe we can just kind of rule that out as a whole class of sentences that talk about themselves, and therefore they're what are called, there's a name for it, they're called self-referential. Self-referential sentences. Maybe self-referential sentences are just a problem in themselves. We don't need to worry about this case. It's not a legitimate sentence. After all, and here's the sort of argument as to why self-referential sentences don't really count as sentences. Consider the sentence, the exact analogous sentence to this sentence is false. It's this sentence is true. Now, this is not a liar sentence. It's not a paradox at all. It says of itself that it's true. But what is it really saying of itself is the question. If it's true, that's fine, but what would it take for it to be true? Just for it to be true. But what about the world would have to be the case for this sentence to be true? It seems like this sentence is claiming that it's true, but the truth of the sentence itself is ungrounded. There's no sort of fact about the world that it's talking about. Since it's only talking about itself, it's kind of meaningless in a sense. And so a lot of people have just rejected self-referential sentences and said that we can still hang on to our law of non-contradiction. Sentences like this should be thrown out for the same reason as sentences like this. They are just an illegitimate feature of language. And indeed, for thousands of years, people thought that was probably exactly the right thing to do here. It's just a problem of English that we're even allowed to utter sentences like this. So what I want to discuss is something that happened about 100 years ago in the philosophy of mathematics, or actually in mathematics more generally, but it was a bunch of philosophers of mathematics. Back 100 years ago, the fields of mathematics and philosophy were much more closely tied. And indeed, they're still kind of closely tied in some ways. What happened was, there was a guy named Bertrand Russell. And so I have a small board here, so I'm going to have to erase stuff. So go and rewind if you want to re-see this stuff. There was a guy named Bertrand Russell, and he was a British philosopher who was born in the 1870s, and he died in the 1970s. He was almost 100 years old when he died. I'll just erase the whole board. Russell and a bunch of other people were trying to work out what we think of as a theory of mathematics. They were trying to work out a way to prove all the truths of mathematics. Prove truths like 2 plus 2 is 4. Now, of course, we know that 2 plus 2 is 4. That's not a secret. But 100 years ago, nobody had ever figured out a way to prove that based on anything more basic. In other words, based on logic alone, they thought they could prove all the truths of mathematics. And this view, which I'm not going to ask you to know well, maybe I will. The view is called logicism. Logicism is the view that mathematical truths can be proven using logic. Logic being just the sort of basic science of formal reasoning. And Bertrand Russell was a logicist, as were a whole lot of people back about 100 years ago. The most famous logicist of all was a guy named Gottlob Frege. And what happened was Gottlob Frege had published a bunch of books where he sort of worked on this project of logicism, of proving mathematical truths based on logic alone. He was a German mathematician and philosopher. And Russell had read one of his books, so his books had great names. The first one was called The Begriffsschrift, which literally means concept writing in German. And then the second book was called The Grundgesetze, which means the groundwork. And in it, I'm not going to go into the details here, but he worked out this whole theory where he could prove that mathematical truths like this were provable using logic. But in order for his theory to work, he needed set theory, what we now think of as set theory. Set theory is just the theory of groups of objects, groups of things. A set could be like the set of people in our class, which would be all of y'all plus me, would be the set of people in our class. Or the set of numbers 1 through 10 would just be a simple 10-membered set. Or the set of erasers in this room, which would be a single-membered set. Or the set of dragons in this room, which is a 0-membered set, which is a thing you can have. And Frege used this set theory to prove mathematics, but in order for him to do that, he needed it to be true that for any property F, there is a set of the things that are F. So for instance, for the property of being an eraser, there's a set of all the erasers. For the property of being a number, there's a set of all numbers. And so on and so forth. This was important because then Frege was going to try to define numbers in terms of these sets. So like, well, without going into details, the number 0 would be defined as the amount of members in the set of all dragons, for instance. I mean, that's an oversimplification. And the number 1 would be defined as the number of sets that have 0 members, which it turns out there's only 1. It's called the empty set. And so on and so forth. Well, Russell comes along, and in a one-page letter, after Frege has written at least 2 very long and complicated books on this subject, Bertrand Russell comes along and he writes a little letter to Frege. In this letter, he says, I love what you're doing, I love your books, I totally agree that logicism is a great thing, and I'm glad you're working on this. And by the way, I found a little tiny problem with your principle here, this principle that for any property F, there's a set of the things that are F. And the problem has 2 famous formulations. I'm going to tell you both of them. That'll probably be all I do today. Let's see, I'm 13 minutes in. Aiming for about a 20-minute lecture, so we'll see how that goes. There's 2 formulations of this problem, and it's known as Russell's paradox, or sometimes it's known as the Barber paradox, because there's a literal formulation of it that deals with math, but there's also a sort of metaphorical formulation of it that deals with a barber. I'll start with the barber. The way it goes is this. Russell simply defines a person. He's going to tell you what this person's like. The person is the barber of Seville. He says, the barber of Seville is a man in Seville, in Spain, who shaves all and only the men of Seville who don't shave themselves. A man in Seville who shaves all and only the men of Seville who don't shave themselves. Okay, so that's no problem on the face of it. It's just a barber, right? Well, it is a problem, because suppose there is such a barber, the barber of Seville. The question then arises, who shaves the barber? Well, if he doesn't shave himself, then he's a man of Seville who doesn't shave himself, and that means, by the definition of the barber of Seville, that he must shave himself. So if he doesn't shave himself, then he does. Because he shaves the men of Seville who don't shave themselves. So if he doesn't shave himself, then he does shave himself. But if he does shave himself, well, he only shaves the men of Seville who don't shave themselves. So if he shaves himself, he doesn't shave himself. Because again, he only shaves the one who don't shave themselves. So if he shaves himself, he can't shave himself. So if he does shave himself, then he doesn't. So, here's a fun, perhaps surprising fact about the barber of Seville. There is no such person. Such a person would be a contradiction. He would have to both shave himself and not shave himself at the same time, in the same sense, and all those problems that Aristotle brought up. This is impossible. So the barber of Seville is impossible. Again, I feel like I should ask if there's any questions, but if there's any questions, rewind the tape and go back and see if I answered them. All right, I can't answer your questions right now. So the barber of Seville can't exist. So he's an impossible person. Now that's a bit surprising that there isn't such a person, that there couldn't be such a person. He's logically impossible. But it's not a huge problem. This is just the metaphorical version of the paradox. After all, prior to today, none of you thought there was such a person. Nobody ever would have thought there was such a person. We've just proven that he doesn't exist, but so what? There's lots of people who don't exist. We've just proven that there's a particular one of them. So Russell's paradox is when you take this metaphorical concept and apply it to something real, and something that's very important to mathematics, namely set theory, that set theory that Frege was using. So this is the real Russell's paradox. And this will basically be the last thing we talk about in 18 minutes now. Okay, so Russell's paradox, the real paradox, comes when you apply the barber idea to set theory. And in particular, when you realize that there are some sets of some sets in mathematics that do contain themselves as a part, and some sets that don't contain themselves as a part or as a member. Now that might sound a little weird, that sets can have themselves as members, but it's actually not all that weird if you think about something like the set of all sets. The set of all sets is obviously a set, therefore it's a member of itself. Again, it's a little puzzling how something can be a member of itself, but mathematicians actually haven't been too worried about this. Sets usually, they're not considered to be physical objects, so having them be members of themselves is not a problem the way it would be like if a cup was inside itself or something like that. It's nothing physical, so there's no sort of problem with this sort of idea. Well, Russell says if you can have a set that has itself as a member, then you can have a set that doesn't have itself as a member. In fact, most of the ones we talk about don't, right? The set of all erasers is not an eraser, therefore it doesn't have itself as a member. Indeed, most of your normal sets that you would consider in any everyday life are not what are called non-self-membered sets. Sets that don't contain themselves as members. So, Russell says, if there's sets that don't contain themselves as members, then there must be, according to Frege's principle, a set of all sets that don't contain themselves as members. Let me put that on the board. So this is the set of all sets. It should be all and only. The sets that don't have themselves as members. The set of all sets that don't contain themselves. The set of all sets that don't have themselves as members. Is there such a set? Well, Russell thinks he knows the answer to that, and he thinks he can prove it. And the answer, he says, is no. Because consider it. If there was such a set, call it delta. This is delta, is the set of all sets that don't have themselves as members. Question, does delta have itself as a member? Well, if delta has itself as a member, then it doesn't. Because it only has sets that don't have themselves as members. So if it has itself as a member, then it doesn't have itself as a member. Because again, it only has sets that don't have themselves as members. So if delta has itself as a member, then it doesn't. But of course, if delta doesn't have itself as a member, then, well, if it doesn't have itself as a member, it's the set of all sets that don't have themselves as members, so it must have itself as a member. So then it does. So, just like the other paradoxes we've seen today, with the barber, or even with the, in a slightly different way, with the liar paradox, if delta has itself as a member, it doesn't, and if it doesn't have itself as a member, it does. Well, look, it's got to be one or the other, so if it's either one, it's both. We seem to have another paradox that flies in the face of the law of non-contradiction, and in the face of Aristotle, basically. Now, for Frege and Russell, at the time when this was first discovered, this was a big deal because it meant that Frege's system wouldn't work. And Frege had already written basically 3 books and published 2 of them on his logicist project. When he got this letter from Russell, it just destroyed his entire life's work. He died considering himself an abject failure, which is kind of sad because he was actually quite successful in a lot of ways. But Russell actually thought there would be ways of fixing this. He spent the next 20 years of his life trying to pursue the logicist project while avoiding this kind of set, saying there can't be such a set as this, but how can we be logicists anyway? And I'll just finish that story for you, and that'll be the end. The way that ended was in the early to mid 20th century, a guy named Kurt Gödel came along and definitively proved, in what was called his incompleteness theorem, he definitively proved that any language of mathematics strong enough to prove things like 2 + 2 is 4 would actually be what's called incomplete. There would be truths of that mathematical system. And indeed, the mathematical system you all learned in high school, or in junior high, or elementary school, or whatever, any of those mathematical systems, they're all strong enough to prove 2 + 2 is 4. And so Gödel proved that all of them are what's called incomplete. That is, there are true facts about that mathematical system that can't be proven using the system. Mathematics, then, is incomplete, but Kurt Gödel, interestingly enough, also proved, the same guy, proved that logic was complete. That is, for every truth of logic, you can prove it using logic. But if logic is complete and mathematics is incomplete, then it turns out logicism, the view that math is provable using logic, is actually just obviously wrong, because logic is complete and math isn't, therefore they can't be the same thing. And so it turns out the whole project that Russell and Frege were involved with here has kind of fallen apart. But the idea that this self-reference, self-reference can work its way into set theory, which is an established field of mathematics, and into mathematics more generally, has really turned a lot of responses to the liar sentence on their heads. This self-reference isn't some flaw of English. This ability to have self-reference is just a natural consequence of being able to express mathematical truths. And as such, these kind of paradoxes show up all throughout language, because English is capable of expressing math, and therefore English isn't bound to have them, but any language is bound to have them, and indeed every language does. And I'll leave you with one final paradox. This is my favorite paradox because it's a paradox in a single word. And I'll give you two words, and I'll define them for you. One is homological. Homological, meaning same meaning, basically. But the definition of the word is, this is a word that applies to itself. Examples of homological words would be, the easiest one, of course, is the word word. The word word is a word, therefore it's homological. It applies to itself. The word short, because short is a short word, and the word pentasyllabic. Pentasyllabic means having 5 syllables, and guess how many syllables it has? It has 5. Pentasyllabic. Just like homological, of course, the English language also has the word heterological. Heterological, of course, is the opposite of homological. This is a word that doesn't apply to itself. For instance, the word long, or the word dog more generally. So a simple example is the word dog is not a dog, so it's heterological. The word long is short, so it's heterological. The word mono, I won't put it up here because I don't really have much room. The word monosyllabic is not monosyllabic, meaning having one syllable. It's heterological. Actually, most words are heterological. So now I will leave you with this thought. I said most words are heterological. Is this word heterological? Is the word heterological itself heterological? And I'll allow you, given what you've seen today, to work out the paradox that's inherent in that question. And I will see you all on Monday, and have a happy Thanksgiving.